Welcome to UGC lecture series Linear Integrated Circuits. In this session we are going to discuss about the instrumentation amplifier, in which the characteristics, the derivation of the gain, applications and transducer bridge amplifier. An instrumentation amplifier is used to amplify very low level signals and rejecting the noise and interference signals. An example can be heartbeats, blood pressure, temperature, earthquakes and so on. So, the circuit which is given here tells you the instrumentation, how the instrumentation amplifier is going to amplify a very low level voltages. Here the input voltages are V1 and V2 given to the positive terminal of a voltage follower circuit. This is actually a voltage follower circuit. Why we are using a voltage follower circuit as one op amp 1 and 2 is to have a high impedance input impedance and low output impedance. So, this is acting as a buffer in the instrumentation amplifier circuit. The basic building block of the instrumentation amplifier is a differential amplifier circuit. In the previous lecture we have seen what is the differential amplifier and how it is going to produce the output and what is the amplification factor, everything. So, here from this, if you divide the circuit into three parts, the last part will be the major the basic building block of the differential amplifier here. So, consider the output of this operational amplifier as V1 dash and here as the second amplifier's output as V2 dash. This amplifier, the third amplifier, is going to be the differential amplifier, which takes the output of the first and second as the input to the negative and positive terminal respectively. That is V1 to the V1 dash to the negative terminal and V2 dash to the positive terminal. And the second block, actually this is the second module if you cut it into three. So, this is the first module, that is AC signal. If you cut the instrumentation amplifier into three, the first is the AC signal. First one has the AC signal and the second portion will have a buffer and third portion will have a basic building block, that is the differential amplifier. So, this buffer is going to connect the input signal which may be in very low level signals, the input signal to the differential amplifier circuit. So, this differential amplifier is going to amplify the difference between the low level voltages V1 and V2. So, since these voltages are very low level, the operational amplifier A1 and A2 is going to be acting as a buffer between the input and the differential amplifier. If it is low, then this resistor R2 and the input resistors R2 will draw all the currents from the voltages or the AC signals V1 and V2 and no signal will get amplified by this differential amplifier. So, we are using an amplifier circuit and this is a non-inverting amplifier circuit. Since we have given the signals to the positive terminal, these operational amplifiers say this is A1 and A2 or the non-inverting amplifiers, or you can say this is a buffer. This non-inverting amplifier will have a input impedance very high when you compare it with the inverting amplifier. So, this is going to amplify the signal and which gives the signal to the differential amplifier circuit. These two amplifiers are acting as a buffer here and this has the high input impedance. So, no signal will be dropped here. So, actually whatever the signal is given at the input, this is actually the amplified version at the output of the differential amplifier. And next is we are going to derive the gain of the instrumentation amplifier circuit by using again the same superposition theorem. Since we have two input voltages V1 and V2 and the operational amplifiers A1 which produces V1 dash and A2 which produces V2 dash. Here by using the superposition theorem, for the first case we have to keep the voltage V2 as 0, only V1 is assumed to be given. At that point the voltage at this node will be having V2 because these two nodes are virtually equal, and if V2 is actually not given, then you have to make this as 0 here. And if you consider only the operational amplifier A1, for that amplifier you have to calculate two output voltages. When V1 is 0, what is the output, and when V2 is 0, what is the output. Similarly for A2 also. For A2, if only V2 is given, V1 is not given, then this node, actually this node feels the voltage whatever given to the positive terminal, since these two nodes are virtually equal. So here it is V1 again. So we have, by using the superposition theorem, we have to split, we have to consider only A1. If V1 is given, then what is the output, and V2 is given, then what is the output. So only for the amplifier A1 you have to calculate two output voltages. Similarly for A2 you have to calculate two output voltages. Finally you have to sum up the two output voltages derived one when V1 is given and V2 is given, and that is going to be the output voltage here, that is V1 dash. Similarly for V2 dash, you would be obtaining two output voltages when V2 is given and V1 is given. So sum up both the output voltages, you will have V2 dash. Then you will be having two voltages at these two nodes, then that is the actual voltage given to the differential amplifier circuit. And we know that for the differential amplifier circuit, again using a superposition theorem, keep V1 dash 0, apply V2 dash and calculate the voltage at this node and find out the output. Again for the next case, keep V1 dash given and V2 dash 0, obtain the output, and finally add all the two output voltages to find out the output of the instrumentation amplifier. So you have to split the module and calculate the output voltages according to the input voltages assumed to be given. Upper amplifier is considered as A1. So A1, for A1 there are two input voltages V1 and V2. So only for A1, if you redraw the circuit, only A1 circuit will be redrawn here. So the signal is given to the positive terminal, which is V1. This is actually A1, the upper comparator, and this is the feedback signal. Take this as R, okay, R dash, and keep this as R, and here V2 is given. Because why I have taken this node as V2 is, this node as V2 and here this node as V1. We know that these two terminals are virtually equal. So whatever the voltage seen by the positive terminal is also seen by the negative terminal. So here V1 is considered, and for the lower comparator at this node V2 is considered. And I have taken this resistance as R dash and this resistance as R. So the feedback resistance as R dash and the input resistance as R, and this output voltage is considered as V1 dash, and which is actually equal to V01 when only V1 is given, and plus V02 only when V2 is given. So we are using superposition theorem. When V2 is 0, only V1 is given. So V2 is 0 in this case. If V2 is 0, V1 is given to the positive terminal. So A1 is acting as a non-inverting amplifier. For a non-inverting amplifier, we know that the output voltage, that is V2 is 0, V1 is given. So we have to consider V1 is given to the positive terminal. So, for a non-inverting amplifier, the output is derived as V01, it is given as 1 plus the feedback resistance R dash by the input resistance R into the input voltage, which is V1. For the second case, when V2 is given, V1 is 0. So, the amplifier A1 will become now inverting amplifier. For an inverting amplifier, the gain is minus R dash by R. So, V02 in this case, the output is represented as V02, it is equal to R dash, that is the feedback resistance divided by the input resistance R into V2. So, these are the two output voltages when V1 is given alone and V2 alone is given. So, now we by using superposition theorem, you have to find out V1 dash is equal to the sum of V01 and V02. So, it is given as 1 plus R dash by R into V1 minus R dash by R into V2. So, this is equation number 1. So, V1 dash we have found out, and V2 dash, that is for the lower comparator A2, again we have to redraw the circuit. So, for A2 the signal given is V2, again the same circuit but with the signal V2. So, the feedback resistance is now considered as the same R dash and here R, and at this point the voltage is V1. So, here the output voltage is considered as V2 dash, which is the summation of V03 plus V04. So, we have again V2 and V1, the two input voltages. So, again using the superposition theorem, we have to find out V03 keeping only one voltage given to the circuit and the other voltage is 0. Similarly, for V04, the remaining voltage is given and the other voltage is equal to 0. So, consider for case 1, V1 is given, V2 is equal to 0. So, if V1 is given to the negative terminal. So, A2 is acting as a inverting amplifier. A2 is acting as a inverting amplifier. The output now it is considered as V03 is equal to minus R dash by R into V1, minus R dash by R into V1. Case 2, V2 is given and V1 is equal to 0, and the amplifier now is non-inverting amplifier since V2 is given to the positive terminal. So, for which the gain is 1 plus R dash by R. So, V04 is given as 1 plus R dash by R into the input voltage V2. The total output voltage V2 dash is equal to the sum of the two output voltages, which is given as minus R dash by R into 1 plus R dash by R into V2. Here minus R dash by R into V1 plus V2 dash is equal to the summation of V03 and V04, it is minus R dash by R V1 plus 1 plus R dash by R into V2. So, this is equation number 2. So, now we have calculated this voltage V1 dash and this voltage V2 dash. So, these V1 dash and V2 dash are given to the differential amplifier's input terminals. Again, by using the superposition theorem, we have to find out the output of the differential amplifier circuit. So, just see the resistor values of the differential amplifier. The input resistors are R2 and the feedback or compensation are equal R3. For A3, consider the differential amplifier as A3, for which V1 dash is given and V2 dash is given. These are the two input signals. So, for the positive terminal, for the negative terminal V1 dash and for the positive terminal V2 dash. Okay, I will redraw the circuit. So, here it is R2, here it is again R2. These two input resistors are equal. This is R3 and the feedback resistor is again R3. These resistors are equal, which is grounded. Here it is V1 dash, this is V2 dash. So, we have to calculate what is the output of the differential amplifier now. So, for which again using the superposition theorem, keep V2 dash 0, apply only V1 dash, calculate what is the output voltage. In that case it is V0 5, and for the next case keep V1 dash as 0, apply V2 dash alone, and for which we have to calculate what is VA at this node. VA is the actually input voltage which is amplified by the factor of 1 plus R3 by R2, and with this VA the output voltage is calculated as V0 6. So, final voltage will be the summation of these two voltages. Again using superposition theorem we have to find it out. So, case 1, when V1 dash is alone given, so V2 dash is 0, A3 is inverting amplifier. Because V1 dash is given to the negative terminal, this is actually 0. So, only negative terminal is given. So, the amplifier A3 is now acting as a inverting amplifier. We know the gain of the inverting amplifier is minus RF by RI. So, in this case the output voltage V0 5, it is given as minus R3 by R2 into the input voltage V1 dash. So, we have derived what is V1 dash in the V1 dash is actually derived as 1 plus R dash by R into V1 minus R dash by R into V2. So, substitute here minus R3 by R2 into 1 plus R dash by R into V1 minus R dash by R into V2, right. So, what is V2 dash? We have to substitute it later. Okay, it is just the reverse, R dash by R into V1. Okay. So, this is V0 5 here, and what is V0 for the case 2? Case 2, only V2 dash is given, V1 dash is 0. So, in that case the amplifier is acting as a non-inverting amplifier. So, the gain is 1 plus Rf by R1. So, the output voltage is represented as V0 6, the gain is 1 plus Rf by R in this case into V in this case Rf is R3 by Rin is R2 and Vin is Va we have to calculate. So, by using the potential divider rule, Va can be calculated. Actually, the voltage across this R3 we have to calculate, but that is the input voltage given to the positive terminal. So, R3 into V2 dash divided by the total resistances R2 and R3. So, here you substitute Va 1 plus R3 by R2 into Va is R3 V2 dash by R2 plus R3. If you take LCM, this will become R2. So, R2 plus R3 can be cancelled. Now, it is R3 by R2 into V2 dash. Substitute V2 dash here to obtain V06. So, it is R3 by R2 into V2 dash. V2 dash is 1 plus R dash by R into V2 minus R dash by R into V1. So, this is V06. So, we have obtained this V05 and V06. Now, finally, you have to add these two equations V06 and V05. This is, take this as equation number 3 and this as equation number 4. So, add these to obtain R3 by R2, that is the feedback resistance divided by the input resistance into 1 plus 2 R dash by R into the difference in voltage V2 minus V1. This is the output of the instrumentation amplifier. So, you have to substitute it, simplify it, and you will be getting this gain. Here the gain is R3 by R2 into 1 plus 2 R dash by R and into the difference in the input voltage V2 minus V1. This is actually the AC signal which is given at the input stage. So, when you substitute it for V1 dash and V2 dash, you will be getting in terms of V1 and V2 alone. So, this is actually the output of the instrumentation amplifier. So, the characteristics is it has high gain and it is very accurate. It has high input impedance and low output impedance, since we have used the inverting amplifiers in the in between the AC signal and the differential amplifier, and it has high CMRR because we are using a differential amplifier. It is going to reject the common mode signal, which is nothing but the noise, which is common to both the input terminals, and it is also having a high slew rate, so that we can achieve a output without any distortions. The advantages of the instrumentation amplifier: the gain of the amplifier depends only on the external resistors, and since we are using an emitter follower configurations, we have a high input impedance, and the output impedance of the instrumentation amplifier is very low due to the differential amplifier circuit at the last stage, and CMRR is very high because of the final differential amplifier. The applications of the instrumentation amplifier are: it is used in the data acquisition from small output transducers like thermocouples, strain gauges, measurements of Wheatstone bridge, and so on. This is just an application of the instrumentation amplifier with the transducer bridge. So, if you look at the circuit, so actually this is the instrumentation amplifier. This is the instrumentation amplifier, and here we are using a transducer bridge, where in one of the bridge arms a resistive transducer is used. So, a transducer which is actually sensing the physical quantity, and it outputs the electrical quantity. It converts a physical quantity into an electrical quantity. So, here the transducer bridge is balanced when by using the VDC supply. So, the output will be actually equal. VAB is actually equal at these two input terminals. There will be an equal voltages seen when the bridge is balanced, and once the physical quantity need to be measured is changed, then the resistive transducer will change its value, and the bridge will get unbalanced, and there is a difference between these two input voltages, and this is actually the input voltage for the instrumentation amplifier, which is going to amplified by a amplification factor of the instrumentation amplifier, or you can say the differential amplifier, which has a high CMRR. So, it is going to reject the noise and it is going to amplify the very low level of input signals in the physical quantity, and it has been displayed here. This is just an example of measuring and controlling any physical quantity using a transducer bridge. So, in this session we have seen an instrumentation amplifier, the characteristics, advantages and applications of the instrumentation amplifier, mainly the gain of the instrumentation, the derivation of the gain of the instrumentation amplifier we have seen by using the superposition theorem. And can you just give me the answer, what is the important function of the instrumentation amplifier? List the characteristics of the instrumentation amplifier and give some applications of the instrumentation amplifier. The main function of the instrumentation amplifier is it is amplifying very low voltages, or it is used for controlling and measuring physical quantities such as the temperature, pressure, heartbeat rate, etc. Thank you.